GH initial equals the same stuff except the final. 1/2 I omega final squared plus 1/2 mv final squared, that's an omega, plus mgh final. All right, what can we get rid of? What's equal to 0?
We can set the final height equal to 0.
Okay. Because Patrick says so. Now what? Assume it starts at rest.
The initial kinetic energies will be 0.
So it's like basically comes down to the same old, assuming it ends with no potential or 0 potential energy, all my potential energy at the beginning gets transferred into kinetic energy as it rolls. All right. So I have mgh initial equals 1/2 I. Well, we know it's I said it was a disk, so 1/2 mr squared omega final squared plus 1/2 mv final squared. So I got 1/4 mr squared omega final squared plus 1/2 mv final squared. What can I get rid of?
Masses will cancel.
All right, so the mass does not matter. But we still have this issue of R here. Well, what's right here? We got R times omega. What's R omega? So we have GH initial is equal to 1/4 V final squared plus 1/2 V final squared, which is 3/4 V final squared. So my final speed is the square root of 4GH initial over 3. The radius drops out and the mass drops out. So the actual shape of the object, the actual value of the moment of inertia does not really matter. Again, it's the relative distribution of the mass. From an energy point of view, if they both start out, if I have two disks that have the same mass, but different distributions of mass, so one's got more on the outside, they start out with the same amount of energy if they have the same mass. But as they go from an energy point of view, the one that has the greater moment of inertia, or the greater relative moment of inertia, I should say, means more energy, a higher percentage of the energy is going to go into getting it to roll, which means there's less energy getting it to move down the ramp. So a higher proportion being concentrated on the I omega squared than the NV squared. And V squared is how fast it's going down the ramp. All right, questions to you? Now, I did play a little fast and loose here. I mean, besides the perfect situation, the perfect rolling. What is the pivot point? What is the axis of rotation? If I have something that's rolling down a ramp, what is the axis of rotation? Or where is the axis of rotation?
Would it be the very center of the?
If it's the very center, then the whole thing is going to rotate about my finger, but it doesn't rotate, it runs into my finger. So it's,
Point of contact?
it is the point of contact. So I've got a disk here where I said, oh, well, I got a moment of inertia, I got the kinetic energy because it's rotating about its center, and I've got the linear kinetic energy here, but it's really not rotating about the very center.
Well, would it be rotating about the center except the center is moving?
I would say yes and no to that one. Let me justify what I did here. It comes out to the same thing. Yeah, we can just, ultimately, that's how it ends up. However, there's a reason for it. If I take my disk and I rotate it about the central axis, you get 1/2 mR squared. If I take the exact same disk and rotate it about the edge, moment of inertia go up or down?
Up.
Why?
Because big R is larger.
Or in general, more mass is rotating farther away. So somehow we need to take into account the fact that this has shifted, but frankly, they have to go through the calculus of this one. Not necessarily a pleasant thing to do. And some textbooks will have this in there, and most of them don't have this one in there. So I introduce you a very useful tool. The parallel axis theorem. If you know the moment of inertia about its center of mass, then you can calculate anything that has an axis that is parallel to it. So I have an axis here, all I did was shift it this way. This axis here is parallel to the central axis. So the moment of inertia rotating about point P is equal to the moment of inertia about the center of mass plus in h squared, where h is distance from center of mass to new axis of rotation. So in this particular case, we shifted the axis a distance of r. So the moment of inertia for this situation would be 1/2 mr squared plus m, because that's the mass that we're shifting, or the mass involved, times r squared. Because we've moved that axis, the radius, and so we get 3/2 mr squared. That is the moment of inertia of this. So if I look at the kinetic energy of something that's rotating about that point of contact, I know that the moment of inertia about that point of contact is 1/2 mr squared plus plus mr squared. What I did over there, I'm just not gonna add them actually together. So if I look at my kinetic energy, I get 1/2 times 1/2 mr squared plus, oops, plus mr squared times omega squared, that's the rotational kinetic energy. Which is 1/2 I, that's just moment of inertia about the center of mass, omega squared, plus 1/2 mr squared, omega squared. And that is just the speed squared. So we have the rotational kinetic energy plus what ends up being 1/2 mv squared, or the linear kinetic energy. So that's justification. You can do it in more generalized terms, but I don't think much is gained.
So you're saying that energy is the same when it rolls as when it just,
I'm saying that for an object that's rolling, even though the pivot point technically is that point of contact, that is the equivalent of just saying, hey, what's the kinetic energy of this thing as if it were rotating about its center, plus the kinetic energy of basically the mass as if it were just sliding down. Questions here? So, thin rod. Rotating about center of mass as shown above. Assume uniform density. The moment of inertia in this case, 1/12 ml squared, or L is that distance there. I would like you to tell me what is the moment of inertia of that same rod rotating about its end, using the parallel axis theorem. I would recommend doing it on paper, but if you want to do it in your heads, some people can do it.
would it be 3/4 ml squared?
Not 3/4.
Well, is H in this case 1/2 L?
Yes. I suspect you just made a careless error. 1/12, not 1/2.
Oh,
That'll do it. It's nice to know I'm not the only one who does make that mistake.
So it's 4/12.
Otherwise known as.
1/3.
Yeah. You don't have to reduce it, but textbooks, when you see this in the textbooks, when they have this particular one, they list it as 1/3 instead of 4/12. All right, so we got the center of mass, about the center of mass, 1/2 mL squared, plus we're shifting the axis half the length. So m times how far we shifted, which is 1/2 L squared. So I got 1/12 mL squared plus 1/4 mL squared. So 1/12 plus 1/4. 1/12 plus 3/12, which is 4/12. With a few stray marks just for color. So now you can figure out moments of inertia of not just the shapes they have, but other shapes. All right, questions to share? All right, I have two objects here, they have the same mass. The difference between them is where the mass is. This one, you can see that, hopefully you can see that this has a hole in it right there. Hopefully you can see light coming through, and this one is darkened. In the middle, this one has the hole, and this one is darkened. That's where the mass is mainly located. So for this one, mass is concentrated on the outside, and for this one, mass is concentrated on the inside. Which one will be easier to spin?
The red one.
Okay. And if you were to try it, you can, but there's the red one, and there's the blue one. And if it's a matter of arm strength, it hurts to do that, so I will stop. Which one's harder to stop?
Is it the blue one?
Yeah. So greater moment of inertia, just like regular inertia. The greater inertia an object has, the harder it is to keep it, to stop it doing whatever it's doing. Same is true with rotational inertia or moment of inertia. So as I was twisting it, what am I doing to it to cause it to twist?
Line torque.
Yes. I would have also accepted force, but that is because that's related to torque. So let's talk about torque. If we transliterate Newton's second law, the F equals ma, we get tau is equal to I alpha. Moment of inertia coming back into it. So for the same amount of torque, the greater the moment of inertia, the less of the angular acceleration, less change to the angular velocity. But how do you calculate torque? Or do you do the Buka? This is total torque. Just like in Newton's second law, this is the total force. So we should be able to figure out how to calculate individual torques. It's nice when the door opens inwards for this next bit. All right. I have a door. I want to close it as efficiently as possible. So the least amount of work on my part, the least amount of energy on my part to get it to close. How would I do it? I imagine you've been closing doors for a long time, so
The farthest from its central axis.
like push on the end.
Yeah.
There we go. Pushing on the end. That's not doing it. There's obviously something more involved.
You need to apply the torque like tangentially to the axis, or to the,
All right, so push like that. That doesn't close it.
well, I guess the other way.
Okay. So whatever it is, we gotta take several things into account. One, I take into account how much force I apply, where I apply it, and the angle at which I apply it. If only there were a formula which took all three things into account. But of course, we are in luck. Torque. The other multiplication of vectors. It is a cross in between them. This is a cross product. We dealt with dot products before. This is the other one, other multiplication. Also known as a vector product. That quotation marks. And